dum. Gitchy, ya, ya, ba, ba. That's the way to start a lecture. All right, so as I recall, last time we did all the types of reactions up through neutralization. Is that correct? Oh, wait, I could just look, huh?
Yes.
When we did that, we did some balancing, we classified, we got decomposition, single replacement, double replacement, neutralization. We stopped there. The one I want to go to now, get back here. The one I want to go to now is I want to show you combustion real quick before we go on to the single and double replacement rules. So let's look at combustion. Now this is some sort of hydrocarbon plus oxygen, and this will always go over to make carbon dioxide and water. We're only going to talk about complete combustion, none of this other stuff. So the big thing about remembering combustion is you're going to have some sort of thing, and it usually looks like a combination of C's, H's, and maybe O's, okay, plus oxygen. It'll always go to make carbon dioxide and water. So if you go to the Wayback Machine to the first day or so in class, we talked about the guy putting his shield over the fire and he got water droplets on it. That's because as the log was combusting with the oxygen in the air, it was given the CO2, and there's your water droplets right there in the form of the H2O. That's where he got his water on his shield. Now, I'll just do a quick little example of this, although we actually already have one as one of our first balancing that we did. I'll do something like C6H11OH. Oh no, yeah, I'll just do that. Plus oxygen goes to make CO2 and good old-fashioned water. Should be noted that these are the ones that will actually go above 6 or could go above 6. So it's okay that we are going to go above 6 for these. Out of curiosity, does anybody want to take a stab at it, or do you just want me to balance it? All right, well, not hearing anything.
It's just
go ahead.
a 3 in front.
Put a 3 in front where?
The CO2.
Actually, I'll go ahead and put a 6 because I have 6 there.
Sorry, I said I would try, but then my internet connection went slow.
That's all right. I'll just go ahead and do it this way. We see we have 12 hydrogens on the left. We have 2 on the right. So I'll go ahead and put a 6 there to make 12. And now if we look at our oxygens, I have 2, 3 on this side. And let's see, 6 and 2 is 12, plus 6 is 18 on this side. There's going to be no way for me to get an even number of oxygens on the left side because I have this odd person out here. So what I'm going to have to do is double everything here. So I'm going to have to put a 2 in front of this. The 6 becomes a 12. This 6 becomes a 12, which means this 18 becomes 36. Now 2 of them are there, which means I only need to get 34 of them. So I'll have 17 times 2 is 34 plus 2 makes 36. So note, combustion can go above 6. Meng, are you here, by the way?
Yes.
Okay, cool. All right. So you'll recognize combustion because you'll have this sort of CHOs or just C's and H's. It doesn't matter. You'll have a lone oxygen doing it there. And on the other side, you should make carbon dioxide and water. That's what we do when we burn stuff. We make CO2 and water. In fact, because we know that, that's exactly how we know how much carbon dioxide we are putting into the atmosphere when we do actually burn something. I do want to make a little side jaunt here back to single replacements here. I want to revisit single replacements. Revisit single.
It's 12 o'clock.
Thank you for 12 o'clock. So the reason why I want to revisit the single replacement is the following. We had copper solid plus silver nitrate, aqueous. And if we recall, of course, the copper is going to go with the nitrate. I told you on the other side, because copper doesn't behave, I told you that it would do copper 2 nitrate, and that would be aqueous. And then we'd have some solid silver. And of course, if I wanted to balance that out, I put a 2 and a 2. Now, the interesting thing about this reaction is if instead I did solid silver plus this copper 2 nitrate, on the other side, we get no reaction. Now that may seem odd because what's the difference? You know, you switch out a metal, you switch out the stuff. Why does it go one way and why does it not go the other? Well, it turns out that some metals are essentially more reactive than others. Means they are more prone to do a reaction than one of their counterparts. And in this case, copper is more prone to doing a reaction than silver is. And there's actually an entire series of these metals saying who is going to basically react with whom or, you know, kick out. So this is how we do it. Let's talk about the activity series of metals. The activity series of metals. Now, essentially, and I'm going to go ahead and write it out just for convenience here like this. This is how it sort of works. That lithium is more reactive than potassium, which is more reactive than barium, which is more reactive than strontium, or calcium, or sodium, or magnesium. So if we look at those, essentially as we go down that list, they become less reactive. I have another line here, and that would be that magnesium is actually more reactive than aluminum, which is more reactive than manganese, which is more reactive than zinc, which is more than iron, which is more than cadmium, which is more than cobalt, which is more than nickel, which is more than tin, which is more than lead. This continues on just a little bit, and you'll see why I'm spacing this out here in just a second. That is more reactive than hydrogen, which I'm going to put in parentheses, and I'll tell you about that in a second, which is more than copper, which is more than silver, which is more than mercury, which is more than gold, or more reactive. Now, the way this reads is as follows. You're going to look at this chart here, and you want to say that the metal, quote, before replaces the ion after. And by the ion, I mean the aqueous. So when we look at this, what we're looking for is, do we see that metal in this long line of list? Do we see that metal before we see the other thing that is swimming around? And so if I look back up, in the first reaction, I had solid copper trying to replace and aqueous silver. So I go down to my chart here, and I say, where do I see solid copper? Right there. Is that copper before the silver? Yes. So since that copper is before the silver, we will replace. In the second one, however, we said we see the silver. Is the silver coming before the copper? It does not. Therefore, it will not replace the copper. Now, if we take a quick look back, I'm going to go ahead and actually access our former notes here. Let's go back to these single replacements. We had magnesium trying to replace hydrogen in one of them. And of course, we already had our copper example. Let's go back to our chart here. If we look at that magnesium with hydrochloric acid, we can see that magnesium comes well ahead of the hydrogen, which means that if whoever hydrogen is with, that magnesium is going to essentially push it out of the way and say, look, I want to be the one reacting here. I'm going to take your partner. We are going to switch. You go do something else. Now, first, do I have any questions about that?
No.
Let me make sure everyone's turned up here. Nobody? Destiny says no, no questions. So you totally got this down, right, Destiny? So my question
I
is,
think I've got it.
what are you going to do when I don't give you this chart? Because I'm not going to. That's for you, Destiny. Hop on. Or are you quaking in your boots?
I guess I have to memorize it.
Nope.
I'm currently trying to look at my internet's unstable. Can you hear me?
Now I can hear you.
So I'm trying to look at the periodic table and understand, like, if you were to say something, is it like if your question were to be like,
Will it or will it not react? Right.
yeah, like I'm trying to look at it and try to get an understanding of how I can look on the periodic table and understand that without actually memorizing the whole thing.
Yeah, I'm not going to make you memorize it because I don't even know them. But what I will say is you're right, April, in looking toward the periodic table, because let's take a look here. No, Vince, you're not going to memorize it. No, Destiny, you're not going to memorize it. No, you're not going to cry. Take a look at everyone here in blue.
Yeah.
Where are they on the periodic table, April?
The group 1
And group 2.
and group 2.
They're groups 1 and 2. Hey, Vince, look at all those green ones. What do we call them?
Transition metals.
Transition metals. And then what about all these guys in purple? Anyone happen to know them? I thought we'd actually said their name once before.
Noble metal? Noble metal?
That is correct, noble metals. Now, if you remember, we said that the noble gases got their name because they didn't react. They also got their name because they were modeled after the metals that don't react, the noble metals, the ones that only royalty could have afforded back in the day. Now, gold and silver are obvious ones to you guys to know that they're, of course, precious metals. And yeah, I could see how those only nobility could afford to have those types of metals back in the day, right? But lesser known are things like copper and mercury. Now, the quaint thing about this is that I've actually gone ahead and put the hydrogen there in red. And we have to remember that hydrogen is a metal. Even though it can do some fun stuff, it is still a metal. Now, how they define this is, will these metals react with hydrogen? Specifically, just like we did over here, this magnesium with the HCl. Will that magnesium kick out the hydrogen? That's what we were looking for. So now, since they are all going to be compared against hydrogen, they can start to make a hierarchy depending upon how quickly they want to react with hydrogen. Now, in general, when we do these, and we had a whole lab on this that we weren't able to do, we actually would have taken, in this lab that you guys were performing the thing on, you saw me take that magnesium and drop it into hydrochloric acid. Bam, it worked, it bubbled, it did its thing. But even more so, one of those guys, calcium, was also dropped into HOH, or water, where even just the hydrogens there, calcium is so reactive, it will actually react with neutral water, kicking out those hydrogens and doing that single replacement reaction. When I was doing some research in grad school, I actually worked with lithium, and to get rid of any lithium I didn't need anymore, I would actually just toss it into some water and just let it go and get rid of it. Because you didn't want to just throw away the lithium, you wanted to take care of it. So even just dropping some of those group 1 and 2s into water is enough to replace the H's even in water. But usually these are based upon like a 0.1 molar acid solution, H solution. Funny side note there, just because if you take a look, you got this guy right here, lead is technically right here before the H. And if you remember, most of our pipes up until very recent times were either made with iron or lead, but we have since made them all out of copper, or now we're starting to use the PEX, but the copper is still widely used. And the reason is because if you leave iron in water, you all know that it rusts, because that iron is going to start reacting there. But also lead will do the same thing. So when they had a bunch of lead pipes, they realized that there were trace amounts of lead leaching into the water supply, because the lead will slowly but surely try to replace the H's in the water and thereby basically poisoning you. So that's why we start using copper, because the hydrogen is coming before the copper, it won't replace it. If it were the other way around, the copper would do it. So that's what we mean when we say the metal before replaces the ion after. And again, for Destiny and Vince, I just want to point out that really what this comes down to in the brass tacks, and this is all I expect you to know, is that groups 1 and 2 are greater than the transitions, which are greater than the nobles. So I'm not going to ask you a question of like, oh, does iron replace manganese? I don't know. I myself would have to come up here and go like, oh, where's the chart? I won't make it that way. I'll make it painfully obvious that it's a group 1 and 2 trying to kick out a transition, or a transition trying to kick out a noble, or vice versa, and see if you can remember which ones are more reactive than others. And again, on the periodic table, it's pretty easy. The first 2 columns, kick out anyone else type thing.
Great. Thank
So
you.
Vince, does that help you there?
Yeah, that helps. Thank you very much.
Yeah. Yeah, I mean, this is not rocket science. I don't want you guys to have to worry too much about it. But so when you go through your lab single replacement stuff, take a look and reason through, why did that reaction actually take place? And keep in mind, just because it wants to go doesn't mean it has to go fast. Remember the silver nitrate with the copper, I think I put on there that it was like 15 or 30 minutes later, right? That took a long time, whereas the magnesiums and the calciums went pretty fast. So just because whether or not it wants to go does not necessarily indicate the speed. If you want to learn all about that, come to Chem 121.
Yay.
All right. So let's talk about the double replacements. Because I told you, you guys are going to have to Tell me this, double replacement. Who is the PPT? Who is the PPT? I said, let's go back real quick. I said, I'm going to give you, say, just this on the left. You won't see anything on the right. It's going to be your job to predict what's on the right-hand side and also who is the solid, who is that PPT. So it's actually not that bad, but there are some rules, the so-called solubility rules. And I hope I actually, okay, I have those printed out. I got that printed out at least. Believe it or not, I'm doing all this with 2 small pieces of paper, my entire lecture here. So double replacements, you want to know who's the PPT? We have some rules here. All right, so some solubility rules. Solubility rules. And it is important that you apply them in order. Meaning, start looking, don't bounce around. Number 1, all sodiums, potassiums, lithiums, and ammoniums, these guys are soluble. So if you happen to have one of those in a compound, you dump it into water, it will go swimming. It will become soluble. I would also say that that extends to H as well. And by the way, there are always going to be exceptions, but these are the general rules. Number 2, all nitrates, acetates, and perchlorates are also soluble. So again, you take a look at one of those compounds, you ask yourself, hey, do I see one of these things in there? If it's there, it's gonna go swimming. These are the 2 big workhorses. Now, let's start talking about some of the exceptions. Number 3, all silver, mercury, and lead. Now, it doesn't matter if it's the 2+ or 4+ version. I'm not going to worry about that. Just remember silver, mercury, and lead. And why is my computer not letting me switch my pens? There we go. I said give it to me. These are insoluble. And when we're done writing out these rules, I'll go through some examples and sort of show you. All right, so we got the sodium, potassium, lithium. It should be no surprise that all those are in group 1. They want to be soluble. All nitrates, acetates, and perchlorates are soluble. Then you get to silver, mercury, and lead, and they don't like to play ball necessarily. Other common things that are soluble, though, is all chloride, bromides, and iodides are soluble. Surprisingly, not so much fluorine. And that is due a lot to its electronegativity. Since it's so greedy, when it decides to start sharing stuff, it doesn't always want to give it up and go swimming. So fluorine is actually not on that list. Okay, number 5. All carbonates, sulfides, oxides, phosphates, and hydroxides. These guys are insoluble. So if you look at a compound and you see one of these guys, be very careful. Most of them do not like to dissolve in water. And I'll clarify that most in just a moment. We got 2 more left. Number 6. All sulfates. Except calcium and barium. Are soluble. And finally, if not here, assume insoluble. Okay, so as I've written this, at this point, I'm going to go ahead and ask Destiny, you got any questions?
So for number 6, was it the SO4 with Ca or with calcium?
Yeah, so if it's calcium sulfate or barium sulfate, those guys will actually fall out of solution as a PPT. Everyone else, smooth sailing.
Okay.
Wow, look at her like not caring. Hey, Vince, you have any questions?
Yeah, I guess I do. What if it's lithium, but it's with carbonate, lithium
Yeah,
carbonate?
so we'll go with that. I figured I would look at your chat question and that was going to be your first question.
Yeah.
Yeah, no. You don't have to memorize them. I also, by the way, will not give this to you. Okay. Again, this is for a little bit more of an advanced thing. I want to point out some trends here, though, so you guys don't just start quaking everywhere and getting all like, oh my gosh, how am I going to do this if I don't have this chart? I want you guys to look at the patterns here. Okay. This is intro chem. This isn't rocket science. I just want you to get the feel for it. So if you look at number 1, all sodium, potassium, and lithium, I've already said those are all group 1. Pretty much, if it's in group 1, it will go swimming. As I normally make you guys do it in a normal class, I'd make you repeat over and over and over. Sodium swims. Sodium swims. Sodium is our workhorse for getting anyone who doesn't want to go into solution to go into solution. And I'm going to show you that in just a second, Vince. Next are ones you just sort of have to have some familiarity with. So the nitrates and acetates, good workhorses again for getting things to be in solution. Sodium swims, all nitrates are soluble. All nitrates are soluble. All nitrates are soluble. Take a look at everything that we had for that lab 6, with all those reactions is every single one of them was like, oh, aluminum nitrate, oh, copper nitrate, oh, you name it. We stuck those guys with nitrates so that they would go into solution. And in fact, if anybody pays attention or if it glances in the back of your brain, when they talk about fertilizers and getting nitrates in the soil and how kind of hard that is to get rid of, is because normally to get rid of a compound, you want to precipitate it out and pull it out of solution. Well, if nitrates are soluble with everything, how do you get it out of solution? There are ways, but they're nasty and they're very difficult to do, which is why in heavily fertilized areas, they actually have problems with nitrate just getting into their groundwater. And if anybody has a heart condition, you know that you take little nitrate pills to lower your blood pressure so you don't get a heart attack. So this could actually have far-reaching effects if it's not monitored very carefully. Now, so the question was, do we have to memorize them? No. Am I going to give it to you? No. Well, what are you going to ask me? I'm going to ask you questions that hopefully should stand out. Now, Vince said, well, what happens if I have, say, lithium with carbonate? Again, we are going to do these in order. So I'm going to, hopefully you guys have that there. I'm going to scroll up and I'm going to give some examples here. Scroll down, sorry. I'm going to give some examples.
I've got another question. You say nitrate is soluble, but what about nitrite?
Very similar, yes, nitrates as well. I'm not going to go through all of them. I'm only giving you guys the ones that are more common and ones that I would expect based on everything I've been writing on the boards and the common polyatomics and the common compounds you'll see over and over in the examples I did in class or in the lab. Yeah, there's solubilities for everything. I just want some of the major ones. So when I take a look at the following, hopefully this will sort of cement it in. So I'm going to do a few of these here. I've got sodium carbonate, iron 3 oxide, aluminum hydroxide, and I don't know, I'll do copper 2 sulfate. And I'll start out with those. What I want us to do is to look at these through the lens of this chart and ask ourselves, is it going to swim or not? Is it going to be soluble? So you said lithium, I'm going to go back to sodium because again, the workhorse here. And I look at my compounds. I have sodium and I have carbonate. Well, as you pointed out, Vince, carbonate is insoluble, but sodium is. Which one do we see first? Applying them in order.
Sodium first.
Sodium, right? So we go down the list, 1, 2, 3, 4, 5. You get, oh, number 1, I have a sodium, done. I'm done. It says soluble, I'm done. I don't worry about anybody after it. When I get to that first thing and it says sodium soluble, absolutely, it is soluble. And we say yes, because of sodium. Now what we're going to do is look at that iron oxide. It's rust. Okay, we all know that rust doesn't dissolve, but why do we know it here? All right, iron. Where do I see it on this list? Oh, it's not here. So number 7, if not here, I assume it to be insoluble. Okay, but what about that oxygen? Maybe the oxygen will make it swim. We go down, oops, nope, number 5, oxygen is insoluble. It's not going to do it, guys. Oxygen at number 5 is before number 7, but it didn't matter. Both of them say insoluble. No, and I'm going to put that for the oxygen. The same thing's going to happen for the aluminum hydroxide. Aluminum is not on this list. It's number 7. Hydroxide is on this list at number 5. Both of them say insoluble. Doesn't matter. So that's going to be no because of the hydroxide. And then we have this copper sulfate, copper 2 sulfate. Again, I'm going to look for copper. Where are you? You're not here. Okay. That's it. As far as copper is concerned, it's insoluble because it's not here. But we see sulfate. 6 comes before 7. And all sulfates are soluble except for calcium and barium. Well, this is copper. So guess what? It is going to go ahead and swim. So in that case, it is a yes because of the sulfate. Now, again, I want to point out that as you go through your labs, go through the homeworks and look at these, take a look at these solubility rules and apply them as needed. But I also want to point out that, again, this is intro chem. And unless I give you the chart, which I'm not going to do because there's no point, I want you to think about the compounds in the class and in your own life that you can think about. And many of them will come to light. We make pipes out of lead. Why do we do that? Because leads are insoluble, right? We make our jewelry out of these precious metals like silver and stuff because they are insoluble. When you get them wet, they don't dissolve. Even our other metals don't dissolve. Iron, cobalt, nickel, all those are not here's, assume insolubles. They're sitting right there. What about some of these more troubling ones? How about this oxide? Well, we just talked about iron oxide, rust. Anytime you oxidize something, it's not going to dissolve. And who sits in the same realm as oxygen? Oh yeah, sulfur. So we see patterns going on here. I've said over and over, calcium carbonate, AKA chalk, marble. not going to dissolve. Phosphate. I said calcium phosphate. Your bones, right? I don't see calcium on the list, but I do see the phosphate, and the phosphate says it'll be insoluble. Now, as you look at these, again, I want you to remember that I'm not going to ask you something that is completely heinous, but hopefully you have either some life experience or just some familiarity with all the ones that I use over and over in class and in the lab. Those are going to be my go-to examples because otherwise it would be impossible for you to do these. 1, does that make sense? 2, any questions?
Makes sense.
No.
Makes sense? All right, is everyone doing okay? All right. So now, let me see if I can remember what to do next. Meng, do you happen to have your old notes sitting there? Because I think the last thing I have is grams to moles.
Yeah, you go to that to the what is his name? Avogadro's number.
Avogadro's number. Okay. So the last little thing we need for this exam is this guy and what he does for us. Okay. So what I'm about to talk about for the next, I don't know, few minutes here is something called Avogadro's number. Avogadro's number. Now, this is what I like to call the most useful, useless number there is. And it's useful insofar as what it does for us, and also because for whatever reason in any sort of high school chem course, the only thing anyone remembers is this number. And I'll tell you why that's useful and then tell you why it's also useless. All right. So by any chance, oh, we are not finding the empirical. No, we're not. Mass. Nope. That's what I'm cutting. Anybody happen to know this number from like a high school chem course or something? Don't remember it? Good.
6.022
times 10 to the 23rd anythings. So what he did is he said, if I have this many of, I don't care what, I'm going to call it a mole, which by the way is abbreviated because we're scientists, MOL. Don't ask me why he called it a mole. Don't ask me why we're so lazy we dropped off an E. But this thing is often called the chemist's dozen. And really, it's just a way of saying, if I have this many things, I'm going to call it a mole. If you have 12 eggs, it's a dozen. If you have 12 cars, it's a dozen. You have 12 people, it's a dozen. It doesn't matter what they are, it's a dozen of those things. And Avogadro says, if you have this many of anything, we're going to call it a mole's worth of stuff. Now, there's a reason why he does this. And the reason is, it's going to act as a scaling factor to basically make what we cannot see suddenly visible. When we look at the periodic table and we look at the masses that we see on those, we look up there at copper at 63.55, we're like, oh, that's how much it weighs. And if you go back to the single version of writing an atom. So let's say, if you guys remember this whole like copper 63 like that, we said that weighed 63, right? Now you might remember that that actually had those units of that AMU. That was the atomic mass unit, and that's if we're talking about one singular atom. The problem here is you can't weigh one singular atom. That's impossible. So what Avogadro says is, look, we need it to be physically measurable, and here's what we're going to do. If you get me 6.022 times 10 to the 23 anythings, it's going to equal something that I'm going to call a mole, and P.S., it's also going to now make it measurable. So I'm going to go ahead and get rid of this copper 63 thing because I don't want your notes to get all muddy, but the chemist doesn't. What this does is this acts as a scaling factor. This acts as a scaling factor to have enough material to actually weigh it. To actually weigh it or even see it. So what this will do is it's going to take those mystical, magical AMUs, take those AMUs from atomic notation, meaning one atom, and scale it so that we can see it. So that we can measure it.
Can you scroll down a bit?
Yeah. Sorry, I just wanted to get where my hand wouldn't crap over. So, and this is where I said back when we did the, was that enough, Rose?
Yes.
Okay. If you guys remember when we were doing those isotopic abundance problems, I said, look, your book's going to say atomic mass units or AMUs. I'm going to go ahead and say it here real quick, but that's the last time we're going to talk about it, because from here on out, we're going to talk about it in terms of grams, something that we can actually measure. Now, specifically, because we're using Avogadro to do this, we are going to make a mole's worth of material. And so really what this does is it takes these AMUs and now converts them into the following. So the AMU becomes grams per mole, otherwise known as grams over moles. So what Avogadro has done for us is taken the hitherto now unseen and say, look, if we have enough of them, we will be able to see them. How many? This big number. Once we have that, we can actually physically measure it. I want to point out we can make some conversions here in just a second and then talk about percents. But why did I call it the most useful, useless number? The useful part is now we can weigh it. The useless part is if you take a look at that number, this 10 to the 23, that means we're moving that decimal 23 places. And I don't know about you, but I have a hard time thinking about anything above a few thousand, maybe even 10,000. If any of you have been to a sporting event, you've maybe seen what 10,000 people might look like. But I guarantee you, even for those of us who live in Napa where there's 70,000 people, we still don't know what that means. You've never seen all 70,000 in one place. And if you did, it would still probably blow your mind. For anybody who's actually seen one of those cool rallies where they might have like 100,000 people lining the streets, that still pales in comparison to this number. This number is so ridiculously large. Let me just point out, that little dot that I just put on the page, that little red dot, if you had Avogadro's worth of those, you could reach the sun if you just laid them end after end. That is how ridiculously huge that number is. Other people have pointed out that if you had a bag full of marbles, I mean, in a really big bag, if you covered the entire United States with these marbles, you would make a mountain 10 times the height of Everest, just because you had a bunch of half-inch marbles. So that's why it's useless, because it is unfathomable. But what it does do is scale everything to where it does now make sense, so that we can go over and say, measure out 1 gram's worth of material. we know that we have a certain amount of atoms of that based on how many molecules are there. Now, here's how we're going to use this grams per mole. Now, keep in mind, a mole is just a thing. It's just a dozen. It doesn't matter. You can have multiples of moles. You can have parcels of moles. Just like you can have a half dozen, you can have a half mole's worth of material. This is as hard as the math gets right here. Let's say that I have 6.35, ooh, gross. 6.35 moles of CO2 is how many grams? And Melinda, if you have your calculator, I'm just making this stuff up again. So I might need to poach you there.
Okay.
So look at this, guys. We're back to conversions. Remember this from the first test? Yay! Forrest, I'm so happy you brought those back. Yay! They're here. So just like any other conversion, we're going to write down where we're going here. So we're going to go to grams of carbon dioxide, and we're going to start with this 6.35 moles of carbon dioxide. The one thing that you need to get through your head real fast, especially not necessarily as much for this one, but definitely the next exam, is that grams are moles and moles are grams. They are the same thing. It's just like saying meters are kilometers and kilometers are meters. It's just a conversion. But you have to recognize that they are one in the same. Now, what we're going to do here is we are going to go to the periodic table, and we're going to know that CO2 weighs 44.01 grams per mole. Now, how did I get that? I'm going to ask Emily. Do you know how I got that?
No.
Okay. Well, we always have to remember this. What is carbon dioxide made up of?
CO2.
What is
Oh,
CO2?
yeah.
Oxygen.
Oh, isn't it just like the mass?
Keep going.
Okay, so it's the mass of 2 oxygens and the mass of 1 carbon.
Yep. So the carbon
Oh, okay.
12.01 grams per mole, and the 2 oxygen is 2 times that 16.00 grams per mole. And you're just going to add those up, which will end up to be 44.01 grams per mole. So the parts equal the whole. So whenever you have any of these compounds, it's not that hard. It's not rocket science. You just go to the periodic table, you look them up, you write them down. Done. Now, remember, this is 44.01 grams per 1 mole, right? So we are always considering this on a per 1 mole basis. Now, that being said, what we can do is put our 44.01 grams of carbon dioxide, because that's what we want anyway. And we're going to put that 1 mole of carbon dioxide on the bottom. That's convenient because the moles cancel. We're left with the grams like we want. And Meng will tell me that's somewhere in the realm of 240, 260 grams.
279.46.
279.46 grams. So if I had almost 6.5 moles of carbon dioxide, it would weigh basically 280 grams. So that's pretty cool. That's pretty easy, right?
Yeah.
Yes, Forrest, it's so easy. Oh, cool. Now, if I can go from the number of moles to the grams, I can also go backward from grams back to moles. So let's do one of those. If you can go forward, you can also go backward. So How about, I don't know, 2.185 grams of, let's go with rust. Fe2O3 is how many moles? And there is a reason why we're doing this, guys. It's going to show its face in the next set of materials. So while it's pretty straightforward right here, let's make sure we got it dialed in. So just like any other conversion, we're going to write down where we're going. So we got those moles over there. So we're going to go to moles of Fe2O3. We know that grams are moles, so we're always going to start with something that looks like what we want. 2.185 grams of Fe2O3. And let's see, Destiny. It's like Destiny, Vince, and Emily are my go-to people here. So Destiny.
That's rude.
Well, and April, but I just have their names in the side over there in the chat. That's the reason why I'm picking on them. Destiny, what units am I going to put on the bottom?
The grams.
Yes, the grams of the Fe2O3. And so on top, I'll go ahead and put the moles of Fe2O3 so that our units are where we need them. And so now we just have to calculate how much does Fe2O3 weigh? And if I remember, it's 159.70.
Yes.
I think I've been doing this too long. So 159.70 grams. And again, that's 1 mole. Grams cancel. We're left with our moles. And that will give me a value of
0.01368.
0.0137. Okay. Now, is it okay to have something less than 1? Absolutely. Just because you don't have a full mole, that's okay. You don't always have a full dozen. And you can also have multiples. So that's about as hard as that gets. Let's see. Just to put one more clarification. So for fun, just to reinforce, Ca3 parentheses PO42. What is its molar mass? And by molar mass, I mean grams per mole. What is its mass on a molar basis? So this grams per mole is also called a molar mass. So someone goes, what's the molar mass? You're just gonna add them all up, right? So parts equal the whole. So that means we have 3 calciums, we have 2 phosphorus, and we have 8 oxygens. Three times, I think it's 40.00 for calcium. Anybody got a confirmation with a period?
40.08.
Oh, 40.08, sorry, yep. Phosphorus is 30.97, I think.
Yes.
And then of course, oxygen is 16. Calcium phosphate happens to be pretty heavy. I think it's in the 300s or so, if I remember right.
31018.
310.18.
Yeah, I think so. If I'm doing it right.
That seems
Yeah.
So no matter what you're looking for, you just take the parts, you sum them up, and you equal the whole. You can do that, and you can do any of these conversions forward and backward from grams to moles or moles back to grams. It's a single step. Don't worry, they'll get more fun next week. Now, one of the reasons why I do this is because when we look at something like calcium phosphate, I actually want to know what is the composition of these relative to each of their parts. So that's going to go into something called percent composition. And this will be our last thing we have to worry about. Percent composition. Okay, so percent compositions are how much of that part within the whole. How much of that part within the whole. And this is always going to be done by mass, okay? If we go back, the only thing we do know is that mass is conserved. It's neither created nor destroyed. It can change forms, but it's the one thing that's immutable. While atoms may combine and you may seemingly lose some things, the mass is always there. So when we do these percent compositions, I'll just remind ourselves how percents go. The percent of anything is going to be the grams of that anything over the total grams. And of course, if you want to make yourself feel good, you'll multiply that by 100 so it doesn't look like a decimal. Just remember that decimals are percents. Now, I'm going to do this by example. I'll just do one example because I think this is pretty straightforward. So example. Ooh, how about let's not make up a word there. What are the percent of lithium, percent of manganese, and percent of oxygen in lithium manganese oxide? This is what I did one of the things I did my PhD work on. Now, all we have to do is figure out how much lithium manganese oxide weighs, figure out how many pieces are inside of that, and divide it out. Does anyone want me to do the calculation for the overall mass, or do they want me to just write down what the total mass of lithium manganese oxide is? If someone wants me to do it, shout.
Can we break it down? What do you mean?
Break it down. All right, so we have 1 lithium plus 2 manganese plus 4 oxygens. That's going to equal our lithium manganese oxide. I want to figure out how much that weighs. So I'm going to take 1 times the 6.94, that's for lithium, plus 2 times manganese, which is 54.94 grams per mole, and 4 times the 16.00 grams per mole for the oxygen, to give me a whopping 180.82 grams per mole for lithium manganese oxide. I can write better than that. Okay, so that's our total. What I want us to do is to figure out how much of that is lithium, how much of that is manganese, and how much of that is oxygen by mass. And so I'll just say that my percent of lithium is equal to my grams of lithium. Well, there's 1 lithium and it weighs 6.94. So I'll go ahead and point it out that that's 1 times the 6.94 grams per mole all over this total of 180.82 grams per mole, and of course times 100%. It should be noted, percents do not have units, and look at that, grams per moles are canceling out. Percents are just a thing. If you do this, it turns out to be 3.84. So lithium doesn't seem to make up very much of this material. If we look at the percent of manganese, well, there were 2 of them, and they weighed 54.94 grams per mole, and the whole thing weighed 180.82 grams per mole.
Real quick, like where are you getting the 3.84? Because I'm trying to do it alongside of you, and I got a 3.8.
You got 3.8 what?
percent for lithium.
Yeah, and I got 3.84%.
Where'd the 4 come from?
I don't know. Do we have confirmation? I'm just looking at, this is the last little shred of paper that I wrote down some old numbers for. I don't have a calculator here.
Okay.
Well, I'll tell you this. Yeah, on the exam, April, you write 3.8 and I had 3.84. You're right.
Okay.
If you told me it was like 17, I'll be like, there's a problem there. But if I have 3.84 and you have 3.8, that's fine.
Okay.
Destiny says, so you're rounding the grams per mole. If we didn't round, we would get the same number. Oh, is that for me or her? I'm not rounding. I never round. I assume you're talking to April. Destiny?
No, I was just wondering, it's for me. I was wondering where you got the numbers, because I'm looking at a different periodic table and it doesn't round.
What do you mean? What doesn't round?
The AMUs.
There are grams per mole in the periodic table now. They're not AMUs anymore. AMUs are for singular atoms, but remember, everything on the periodic table is all of the atoms. So that's all the isotopes. So those are no longer AMUs. They're the average of everything, which now makes them grams per mole. So what periodic table are you looking at that differed from mine? What was
It's the
different?
one that I found on Google.
Sure. What was different?
So like oxygen, it says 15.999.
9999998. Right?
Right.
Yeah.
So just round that.
It's not gonna do a damn thing to your numbers.
Okay.
So I usually go out 2 decimal places. Most normal people are gonna go out 2 decimal places. If you're having to go out those 6 decimal places, you're in the high country. So it won't matter if, and I'll give you, remember, I'm gonna give you the periodic table. It's gonna look exactly like the one in your book. And it's only gonna go out 2 decimal places. So, so don't worry about that. Manganese will turn out to be 60.77. The percent of oxygen, that's 4 times the 16.00 grams per mole divided by the 180.82 grams per mole, of course, times 100%. That should leave you with the 35.39% for oxygen that is left over. That's as hard as that gets, guys. Now, I do want to point out just real quick, and I'll scroll it back up for you, Destiny, in just a second. Notice that it looks like most of this thing is manganese, but in the compound, it looks like there's 4 oxygens, and they should be dwarfing everything because there's 4 of them to 3 of the others. Remember, when we do the compound formula, it is a ratio of atoms. And if we go way back to Proust, we said it was a small whole numbered ratios based on their masses. And so these LiMn2O4, those are the atomic ratios based on how much they weigh. And that's why manganese actually makes up the lion's share of the mass of lithium manganese oxide, even though there's only 2 of them. They're just heavy. Okay. So, what did we learn today? We learned that there's a way of determining whether or not a single replacement is going to occur. We had this guy, groups 1 and 2, greater than the transitions, greater than the nobles. Make sure whoever is the metal, that it comes before the one floating around. Otherwise, it's not going to work. Double replacement. We had a complex set of rules here that hopefully boil down to this. Sodium swims. All nitrates are soluble. And then worry about the rest of them. And we learned that this Avogadro's number turns anything into a mole, and those moles are now measured in grams. We can do a couple of very simple conversions there, just making sure our units go. And of course, we can get the percent composition by taking everyone's part over the whole. That's it. I do want to give you guys one little cautionary tale here, especially because it's Chem 110. Let's go back to the balancing reactions. Where are you? There we go. Let me grab my glasses again. Take a look here at our double replacements. And I did it on purpose so that you didn't think it's the last one that's always the solid, but sometimes the first one. When in doubt for this class, take a look right here. Sodium nitrate. Is that soluble or insoluble? Forget about the AQ out of there.
Soluble.
Yeah, it's going to be soluble. Why? Well, sodium swims. Oh, all nitrates are soluble. So if that's the one swimming, guess who's not?
The other one.
All right, I'm not going to trick you guys in this class by giving you a reaction that doesn't occur because nobody falls out of solution. That's not the goal of this class. This class is to say, can you tell me who's the precipitate? The easiest way, look for who's swimming, and if that one's swimming, it ain't the one doing the precipitate. Look at the next one. Is the magnesium phosphate or the potassium chloride the one swimming? Well, potassium looks like sodium.
Sodium.
Sodium swims, so KCl is swimming, so guess who's not, right? So look for the one that is, still swimming, and it's the other one that's not. So that's a good little safety tip for me on there. Okay, that is the end of this lecture. Yay! Do we have any questions?
I don't think so.
Okay. Again, I'm going to try to find a way that we can upload our stuff through Canvas for our exams. I'm going to be talking to some people this afternoon about how that can happen instead of having to email them. And I'm also going to have some instructions about how to make smaller versions of your PDFs so that my overly text internet can actually do it. And so we'll go from there.
Okay, well, we'll be able to print out the exam like last time?
Yes,
Okay.
you will. Yeah, and there's gonna be some other directions there too, like please actually write out the question, because there were some times your answer was like increase, and I'm like, wait, what? And so it was sometimes a little difficult for me to figure out what's going on. So I'll have some other instructions if you can't print it out about what to do. But yes, I'll be making one that you can print out so you can do it and then take pictures.
And this will be Wednesday morning and timed again, correct?
Yeah. I'll probably do the same thing. It'll be open from 8 to 12. You'll have an hour and a half because of the time involved in picturing it and PDFing it and uploading it. So that should be plenty. ¿Más preguntas? All right. Well, I am going to stop the recording.